The arc length of a parametric curve can have many different uses, and one of these uses is in regards to football routes. Let's go into this interesting website here by AWS Next-Gen Stats that gives us the route trees, QB targets, and running back runs of every single top player in every single game. Let's take, for example, Zach Ertz. He's a tight end for the Washington Commanders. And this is his route tree from Thursday Night Football against the Eagles on November 14th, 2024. Now, every route on this chart can be represented as a vector. Think of a vector as an arrow. It has a direction and a magnitude. So for this example, the crossing route can be described as a path that starts at the line of scrimmage and bends across the field. Now, at this point, you're probably confused. How can a vector be curved? Well, let's go into a little bit of the calculus of vectors. Now, first of all, vectors themselves don't curve in the traditional sense. As I said before, they have a magnitude and a direction at a specific point in space. But when you talk about a curved path, you're describing a series of vectors whose direction and magnitudes change smoothly along the route. So instead of a vector, it's really a collection of vectors that form a vector field or a parametric curve. So in the case of the routes we see here, the curves represent the paths that Zach Ertz runs, and that can be described using vector calculus. So let's go back to the context of Zach Ertz's route. The football field which he's running the route on represents a 2D plane with the x-axis running sideline to sideline and the y-axis running end zone to end zone. As Zach runs his route, his position changes in both x and y, forming a path described by a vector function. So our vector function is really a parametric function which has a parameter of t. So r of t, which is our vector function, is going to be equal to x of t, comma, y of t. Now that we have a representation of the parametric curve, we can now find an actual equation for the parametric curve and find the arc length. So I went ahead and designed our parametric curve here, and graphing this would give us a representation like this. The purple part represents the route itself, and the green part represents the yards after catch. Overall, it looks pretty similar to our original route. Now let's finally use the arc length formula to find the arc length of this parametric curve or this route. Since we already know our x of t and y of t, all we gotta do is find the derivatives of them and plug it in. For our integral components b and a, b will be set to the final time that Zach is running the route, and a is the initial time at which Zach is running the route. So after plugging in everything into our equation, we can finally get our answer for our arc length. And our final answer would be 5.781. But what would the units be? Well, on our graph, our x went from 0 to 4 and our y went from 0 to approximately 1.8. Keep in mind that at the beginning of the route is where Zach Ertz starts at the line of scrimmage, and at the end of the route is where Zach Ertz ends up out of bounds. So we take the actual game footage of this play itself. At the beginning of the route, it looks like Zach Ertz is lined up about 2 yards away from the right hash of the field, which is 18 yards away from the out of bounds line. And on the play itself, Zach gained about 9 yards, as you could see from the clip itself. If we took these horizontal and vertical values and divided them by the units on the graph, we get these values. And from this, we can get a graph that's a lot more representative of the route itself, as we can multiply these scale factors by the vector component. And with this, we get a lot more accurate of an answer of 26.732, with the units being yards. So in conclusion, we could say that Zach Ertz on this route covered about 26.732 yards as he was running to get the first down.